whatever is configuration.
Can I explain it?
Yes, because like I don't understand it whatsoever.
Um, okay. Let's see if I can find a thing to show. Um, so I have stuff about that in that first ACS review PowerPoint. Okay, which I just downloaded twice by accident. All right, that's great. So there's a lot of pieces and parts to electron configurations. A buffer is a weak acid and its conjugate base. What? Okay, Zoom is telling me I can't open PowerPoint until I leave the meeting and come back. So I'll be back in a second. Okay. I had a little issue this weekend. My computer decided that it wouldn't charge anymore. And you can't really have a laptop that doesn't charge. And so we had to go out and immediately buy a new laptop. And it's not used to everything yet. So I have a lot of, I don't know where to start with the electron configurations because there's so many parts to it. So I'm going to start with this picture, which puts the order of the electrons on there, right? First you have 1s electrons, then 2s, 2p, 3s, 3p, 4s, and then 3d. Is that something that makes sense?
Yes, ma'am.
So, okay, so you know that that's true. And then that goes along with the periodic chart. So if you look at this picture, anything that's got electrons starting off in those first or any element in these two columns is filling in s electrons. So hydrogen starts and actually it starts on it starts with hydrogen and helium, but then the next one is lithium, which is right here, and then beryllium, which is right here. And lithium is the last electron is 2s1. Beryllium, the last electron is 2s2, 2s squared. Doesn't want to do that. So here's lithium. Ooh, And how come it's only showing one electron or one? Okay, so lithium has 3 electrons. The first 2 go into this box for 1s, one pointing down, one pointing up. Ms equals -0.5 and +0.5. And then the third one goes up into this next box, the 2s. When you get up to something that includes 2 p's, you have to consider more issues. Carbon has 6 electrons because it's the 6th atom. And so you would fill in 1, 2. Can I draw them? I don't know. Okay. Nope. Why don't you want me to draw? It's not giving me a pen. Okay. I'm going to use Zoom to do it. So you get 2 electrons here, and then the next 2 electrons go here. So that's 4 out of the 6 carbon electrons. And then the 5th electron goes here, but then the 6th electron goes here, because there's this rule called Hund's rule that says you put 1 electron into each of these boxes because they're all in the same level. And once those are full, then you go back and fill in the second one. Does that sound familiar?
Yes.
Okay. So then carbon would be written as 1s squared, 2s squared, 2p2. Somebody just asked if they can turn in their exam without a Scantron, and no, that can't work. You can't write on the exam booklets. You have to fill it out with a Scantron. So that's some things about electron configurations. I guess without more questions, it's hard for me to know what your question is.
I just wanted a better understanding because I believe it's quiz 1, like the review quiz. I couldn't even get through the first question because I didn't understand the electronic configuration.
Well, have we addressed any of the things that you were wondering about?
Yes, ma'am.
Okay. And I guess what I could do is I could go to this review quiz. Look at some of these questions. Electrons in an orbital with L equals 3 are in a, the answer is S goes with L equals 0. I'm holding up one finger. S goes with L equals 0. That's the first one. And a 0 is round, just like an S orbital. L equals 1 is a p orbital. L equals 2 is a d orbital, and L equals 3 is an f orbital. So they go in order S, P, D, F. And since we're talking about L equals 3, that should be an F. No 2 electrons in an atom can have the same 4 quantum numbers is a statement of the Pauli exclusion principle, which says you can only have 2 electrons in an orbital. One of them has ms plus a half, and the other one has ms minus a half. And the other 3 quantum numbers, n, l, and m sub l, specify which orbital you're talking about. So up through m sub l, you're talking about the orbital, and then m sub s is which electron are you talking about, the up orbital or the up electron or the down electron? Whew, I can't do this one without a periodic chart. How many neutrons are there in an atom of lead whose mass number is 208? I think that lead is element 82. But I have to pull up my periodic chart to see. The other part is that I can't connect my iPad to this new computer because it has a completely different thing to plug into it. So they won't, I don't think they'll talk to each other. I might be able to, I don't know if I can screencast to it or not. I'm just unsure. So lead is 82. And so how many neutrons are there in an atom of lead whose mass number is 208? It would be 208 minus 82, which I'm going to guess is the 126, because 8 minus 2 is 6. I don't know, I'm not coming up on electron configuration questions here. Protons and electrons. It's fine. We'll skip. Oh, here we go. What is the maximum number of electrons in an atom that can have the following set of quantum numbers? Anybody want to guess? First of all, is it allowed? N equals 4, which is fine, and L equals 3. L can go up to n minus 1, so this is okay. M sub L equals -2, and M sub L can go up to plus or minus L. So it could be plus or minus 3, but it couldn't be plus or minus 4. -2 should be fine. And M sub S is plus a half, so that's okay too. That means it's the spin up electron. And the answer is that only one electron can have all these quantum numbers because that specifies an exact electron. If you have all 4, there's only one. That was in that previous question we just looked at about the Pauli exclusion principle. So it should be 1. That's another mass number question. Okay, here we go. Which one of the following sets of quantum numbers is not possible? Any guesses? No guesses.
On the one on row 3, is that supposed to be a plus sign?
Yeah, it's just kind of faded looking.
Oh, okay.
Yeah, it's this one right here. Oh, sorry. I was trying to highlight it and just moving it. Nope, only highlights the whole thing. Row 2. We can't have this combination right here because M sub L can only go as high as plus or minus L. And since L equals 0, the biggest M sub L you can have is 0. So row 2 is the bad one. The other 4 should be fine. Oh, and now I have a pink circle. Okay, atoms of the same element with different mass numbers are called isotopes. It's another one of those. Okay. Here we go. Which ground state atom has an electron configuration described by the following orbital diagram? We're talking about 3 S's and 3 P's, so we're in the third row, and it has 3 P electrons. Well, I don't know that I can. No, it won't do that. Okay. Nope, I can't do that either. That's terrible. Let me see if I can pull up a periodic chart to make this obvious. Okay, so it says 3, let's look at the picture again so I don't get this wrong. Oh, there's 2 3s electrons, so it's 3s squared, 3p3. There's 3 electrons in p orbitals. So first of all, we have, it starts off with neon, so then we go down to the third row, 1, 2, 3, and we have both of these electrons, 3s squared, and then we have 3 p electrons, 1, 2, 3. So we're talking about phosphorus. So that might be a question that was more along the lines of, here's an electron configuration question that's maybe kind of difficult. I mean, it's not difficult if you know what you're doing, but maybe that you hadn't practiced recently. So let's look at that picture again. Right. So neon, 2 3s electrons, and then 3 electrons in the 3p level. And so that would be, we're past neon in the third row, 1, 2, and then 1, 2, 3 p electrons. So definitely phosphorus. And really, the periodic chart is how I do electron configurations. So like, if you wanted to know what the electron configuration for vanadium was, right here. We'll have to get those things back. Let's do blue. So we're talking about vanadium. First of all, the row before it ends with argon. So this is the worst. Argon. And after argon comes, there's the 1, 2, 3, 4s, and there's 2 of them. So 4s squared. And then there's 1, 2, 3d electrons. 3d3. Okay, let's go to the, oh, I didn't answer it. We said it was phosphorus. There we go. Give the number of protons, electrons, and neutrons in one atom of chlorine-37. Oh, it's another one of those isotope questions. Okay, so we did a lot of stuff just now on electron configurations, and I'm going to stop because somebody may have a different question.
Do you mind if we go over the intermolecular forces, like the dipole, and then all of those type of things?
Okay, so here we are on intermolecular forces. And so they're all listed on this page right here. Intermolecular forces are van der Waals forces. There's three kinds: dipole, 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 induced dipole, and induced dipole, also known as dispersion, and also known as London forces. So this thing right here has like three names, four if you count the van der Waals part. And this is the one, this induced dipole is the one that every single molecule and atom has with every single other molecule and atom, because you don't need to have a dipole to have it. And even if you have a dipole, you also have this going on. This is in everything. And the fourth one is hydrogen bonding. The way that the induced dipole effect arises is that when two molecules become close to each other, their electron clouds will interfere with each other, and one of them will slightly move to one side while the other one moves in the opposite direction, meaning that the molecule in front will be positive on the left and negative on the right where the electron cloud is shifted, and the opposite will be true on the one next to it. But when a cloud shifts, if like a water wave shifts one way, it's going to have to shift back the other way. And so when it shifts back the other way, the positive and negatives on both molecules flip, and they're still attracted to each other. So this movement of electron clouds allows constant attractions between two molecules, even if they don't have a dipole, because the electron cloud is made of moving charges. And so you can have that happen. Induced dipole is most important with heavier molecules because they have more electrons. The shape is important. Long, skinny things have much higher attractions than round things because the round things can only touch at one spot, and long, skinny things can touch over, they just have more surface area and they can be in more contact with each other. Dipole happens when there's a dipole moment, and that arises from different electronegativities of the different atoms that are involved. And there also has to be a certain amount of lack of symmetry. It has to be bent in some way. Otherwise, if it's perfectly symmetrical, then everything offsets and you're back to having a nonpolar molecule. But the dipole is in addition to the London forces. So they're about the same size, but when you have the dipole, they stack on each other. So they're twice as attractive as things that are nonpolar. And then hydrogen bonding can add on the top of both of those. And those only occur between hydrogens on O's, N's, and F's attacking another O, N, or F.
Okay, so one of the exam one problems, it says, which of the following intermolecular forces are present in liquid water? How do we know how to find that?
Well, you know what a water molecule looks like. It's bent. It has a dipole moment. And we talked about hydrogen bonding constantly with water. It has H on an O, and there's other O's in there. So it definitely has that. Hydrogen bonding, we know it has a dipole. Everything has induced dipole. So it has all of those. If I go back, where's the specific question? Exam one. I think I have it open already, right? Yeah. So the answer is D, all of these, because we know what water looks like. We know it's H2O. We know it has hydrogen bonding. I mean, hydrogen, that was what I was like half a lecture on how water has hydrogen bonds and it holds itself together better than basically any other liquid.
Okay,
It
thank
doesn't
you.
evaporate as easily. Shoot, where did that, oh, sorry, that was on the PowerPoint. Yeah, the intermolecular forces of liquid water mean that we can keep our oceans, even though the temperature is only like, you know, what it is on our planet, and the gravity is actually pretty low. Water is only 18 grams per mole, and a lot of things that are 18 grams per mole-ish are light enough to go way up into the atmosphere and disappear into space. But water doesn't do that. It's got such strong intermolecular forces, it stays in the liquid state. Oxygen, O2, weighs way more than water, but it doesn't have strong enough intermolecular forces to make a liquid at room temperature. So water is super important. Without it, we wouldn't be alive. We wouldn't have a planet. We'd have a planet, but we wouldn't live here.
Okay, this will be my last part to that question. So what would be like what would be the forces, for an example, like ammonia? I don't know if that's a good example, but what would be the forces present, like in ammonia?
Well, ammonia has hydrogen bonding also. It has N and an H in it, and that'll attract to the lone pair on a different nitrogen. So it definitely has hydrogen bonding. It's a trigonal pyramidal molecule, so it is asymmetric, and nitrogen is electronegative compared to hydrogen, so it's going to have a dipole moment, so it'll have A, and everything has letter B. The induced dipole is in everything, even argons, even heliums.
Okay, that makes more sense. Thank you.
Sure. Right. So in the next question, which one will have hydrogen bonding? It's the ammonia.
Wait, Doctor, I have a cool question. Were those quizzes also a part of the quiz amnesty thing?
Which quizzes?
The quizzes for review?
No.
Okay.
Those are not for points. Those are just, you can do them in it as a study aid. But they're not actually part of your grade. And then the amnesty ended, right? It was done at 8.
Yeah. Also, I have a question about like the delta HFs and like those things. It was recently on test, but I just needed a quick review off of those things.
I guess I'm not 100% sure which type of question you're asking on that, but so in chapter 6 of the Chang book, it's all about energy, heat, and enthalpy. And enthalpy is what the H stands for. The full definition of enthalpy is it's a combination of energy and pressure times volume. So when a system in the lab heats up, it always expands a little bit. And so the amount of heat we put into it raises its temperature, but also when it expands a little bit, it does some work because it pushes on the atmosphere. And enthalpy accounts for both of those two processes. So that the amount of heat that you put in accounts for how its temperature goes up, and also about the work that it does against the environment. So you know that delta H positive, greater than 0 is endothermic, and if it's negative, it's exothermic. And then there's reaction enthalpies that we can calculate. So this thing that's right here on the screen is called a thermochemical equation. It shows you the chemical reaction and then the delta H that goes with that reaction, the enthalpy of the reaction, right? And so there's 3 of them on this page. Oh, I don't want to do that. We wanted to, so I think this is what you want to do. So a standard reaction enthalpy with the little 0 on it means that when we start, we have those substances pure, and any gases at 1 atmosphere. I think actually they changed it to 1 bar, but it's almost exactly the same. So solids, liquids, and gases are pure. Solutions are always at 1 mole per liter. And so that's what gives you the little 0 thing on it. And mostly it's about that pressure is 1 atmosphere thing. And Hess's law says that enthalpies are additive. I thought I had a good question in here. Oh, maybe it's the next one. Right. Okay. So here's an example reaction. Carbon plus oxygen gives you CO2, and delta H is -394 for that. This is the delta H of formation of carbon dioxide, because you've got elements in their standard states as reactants, and you have 1 mole of carbon dioxide as the product. But you can do this in 2 steps, where you do, first of all, you react it with half a mole of oxygen and you get carbon monoxide. Since you're only halfway there, the enthalpy is not as big as burning all the way to CO2. So delta H for this first step, that's the enthalpy of formation of carbon monoxide, delta HF is -111. And on the second one, carbon monoxide is combined with half a mole of oxygen to go to CO2. And delta H for that is -283. And if you add both of these together, you get the whole reaction. And if you add both of these 2 reactions together, you get this whole reaction. Because you've got carbon and a half mole of oxygen and a half mole of oxygen. You're making CO2, and there's a carbon monoxide on the reactant side and on the product side, and they cancel out. And this process where you can combine reactions and their enthalpies to give you the final reaction and the total enthalpy is called Hess's law. And I think this one was meant to be right. You can combine these 2 to get this top one. But I don't know if I answered the question that you were asking. That's some stuff about enthalpy and enthalpy of formation.
Yeah. I also wanted to know about delta G.
Okay,
was it delta G? Was it something about it being negative? See whether or not it was delta
spontaneous?
S. Yes.
Delta, right. So if delta G is negative, then you have a spontaneous reaction. That would be in the free energy notes. So delta S of the universe is, my screen sharing is paused. Uh-oh. Okay, so delta S of the universe being positive gives you a spontaneous reaction. And that's a combination of change of S of the system and change of S of the surroundings, which we know is minus delta H over T. Well, because it's really complicated to think about the universe every time we want to decide if something is spontaneous, there's a switch that people do to this other function called Gibbs free energy. And it's basically delta S of the universe multiplied by negative T. When you do that, the delta S becomes negative T delta S, and the negative delta H over T just becomes delta H. And because you've multiplied by negative T, although delta S of the universe is positive for a spontaneous reaction, delta G is negative for a spontaneous reaction because it's the opposite of delta S of the universe multiplied by T. So this bottom yellow equation is sort of the take-home message on this slide. Delta G is delta H minus T delta S, and if delta G is negative, the process is spontaneous.
I have another question. So since you said we need a Scantron for we can't write on the test that you're giving us, are we able to bring like scrap paper?
I'm going to provide you with 2 pieces of scrap paper per person to
Okay.
yes. But if you need to bring your own, you can. You just have to turn it in with the exam. But I will be giving every person 2 pieces of scrap paper. Okay. Anything else about delta G? Like, that's the specific question that you asked, is how it relates to spontaneity. Like we did this. Oh, that one doesn't have delta G on it. Oh man, I thought I had another one. I do have another one, but it's in the chapter 18 notes that we didn't get to. So to find the spontaneity of a reaction, you need delta S for the system. You need delta H for the system. You need the temperature. And if you combine those 3 things together, you can get delta G, which tells you that it's spontaneous using this yellow equation.
I have another question. So I was going over some of the quiz questions, and it was talking about determining whether the reaction was endothermic or exothermic. So can you just like give a little bit of explanations how you could determine which one, like the difference?
How you can, I need a little bit more specifics on that. Like, did you have delta H values?
No, I'm talking about like if they just gave you a regular chemical reaction, and then like based off the reaction, you have to determine whether it was exo or endothermic.
Yeah, I need more information so I can narrow down what the context was.
I don't know how to explain
Was it on a review quiz? Was it on a?
It was on a review quiz, but I don't have the question up anymore. It was like something about H2SO4 and how do you determine it was endothermic or exothermic. Like, I don't know how to explain it, but hold on, let me see if I can find a question online.
So I'm trying to do the run through the quiz really fast. It's going to be hard. Okay, I got it. This one?
Yeah.
So burning in oxygen is combustion. And I don't think I know of any examples of an endothermic combustion. Just the whole term, kind of implies giving off heat. So reactions where something is combined with oxygen, burning, you can peg right away as being exothermic. The next one that isn't a combustion, water in the gas phase going to water in the liquid phase. So that is the condensing of a gas to a liquid. And it's hard to think about that being as endothermic or exothermic. So what I do is I think about the opposite process, a liquid going to a gas. How do we make liquid water turn into a gas? We have to stick it in a pot on our stove and heat it up. And that means that process must be endothermic because it doesn't give off heat. We have to pour heat into it to make it happen. Oh, sorry. I was talking about the opposite one. So the opposite, liquid going to gas, being endothermic, means that the gas going to the liquid is exothermic. And so the last one on this page is water in the solid phase going to the liquid phase. Well, we know that for ice to melt, which is this last one, like you have to warm it up. You got to stick it in your hand and you can feel it melting, right? It's taking the heat out of your hand in order to do that. This is the endothermic one. Does that reasoning help?
So you're basically saying that if it's endothermic, it goes from like solid to liquid, and if it's exothermic, it goes from liquid to gas? Well, solid to gas, is that what you're saying?
Solid to liquid is endothermic. Solid to gas is also endothermic. It's the liquid going back to the solid that would be exothermic.
Oh, okay. Okay.
Right. If going in one direction in a reaction is exothermic, then the other direction is endothermic. Because they're opposites of each other.
Okay, thank you.
So if you don't recognize what combustion means, this question is impossible. But the assumption is you know what combustion is. Any reaction where you're combining with oxygen to make products like water and CO2 or NO2, that's basically the reaction for setting it on fire. And it would be exothermic. And then so melting and freezing and boiling, we have talked about them in my class as well, but they're also back in a little bit in part 1 in chapter 6. So I don't know if there's another one that's like that or not. Oh, there's another Hess's law problem. I would also say that, I gave you like 20 questions, 15 questions over this topic, and the final cannot do anything like that. I mean, there might be 3, right? Because it's 70 questions covering the entire year. So it's not, they can't spend this many questions on one topic. Something's in the chat. Endothermic is heat is a reactant. Yes. Exothermic heat is a product, like a flame is giving off heat. Any other? I don't even know who all is here. Okay.
Dr. Reese.
Yes.
Hi. You might have mentioned it. I had to step out for a second, but I did send you a chat about an email that I sent. If you can just check it when you get a chance.
Yeah, I saw it.
Okay, thank you.
Okay. Any other final exam questions? Take your time. Use your scrap paper. It really does help to write down pieces of questions on scratch paper, because the thing that gets you twisted up, other than just not knowing the answer or how to do the problem, is trying to manipulate too many things in your head and not using your paper as a place to put pieces of the information. That harder questions are not usually harder because the topic is harder, but because there's so many pieces to it that you can't keep it all in your brain at the same time. Humans can only juggle 4 different things in their mind simultaneously. So if the question has 5 things, you have to use paper or you can't get through the whole question. And, you know, I'm giving you this paper for free. You're not wasting any money by filling up all 4 sides of those 2 pieces of paper. And I have to shred them when you're done. So there's no reason to save it. Use it all up. I don't know, maybe that sounds stupid, but I have been to these discussions where they talk about the neuroscience of learning, and the biggest thing is people trying to do too much in your head and not using these external things to help you work through a question. It really does help. The other thing is, you don't have to get 85% of the questions right to get an 85 on this exam. I don't have the exact number in front of me, but the national average on this exam is about a 60. And I consider the national average to be about a B, so like an 82, okay? It's like a B minus. Oh, in this class, it's a little bit lower because in this class, a B minus is a 77, right? Because 75 is the bottom of a B. So if you can hit 60%, then you're going to have a B. And then I use the standard deviation to see how many more questions you can get to an A. And I haven't looked it up. I'm sorry. But it's probably about 7 or 8 questions to get up to an A from there. But then it's also 60% minus 7 or 8 questions to get down to a C. And another 7 or 8 questions to get down to a D. So I use, we can't use the straight percentage number because people all across the country take this exam. Some of them have had terrible chemistry classes and they don't do great on it. And so that only, a lot of people will skip a topic. We skipped one topic at the end here because we never got to it. And that is taken care of by the curving. It's not taken care of by me subtracting questions because that actually messes everything up. But it is taken care of by the curving and the norming. So just do your best. There will be a few questions that are things that we didn't cover. That's okay. Answer them anyway, because a wrong question does not subtract from your score. It doesn't add anything to your score, but it doesn't subtract anything from your score like on the SATs. So answer every question, even if you don't know. And, you have a 25% chance of getting it right. Any other material questions? I hope everyone does their best, that you get at least some rest so you can think clearly in the morning. I know there's a lot of, what's the right word, administrative questions, and I'm really not going to answer them until after I've got the final exam graded. So if I don't answer your question about how many points this or something like that, I got to get some stuff graded, so I'll get to it. Okay. If there's not another question, then I'm going to say goodbye and good night.
Thank you. Good night, Dr.
Good night. Thank you.
Thank you. Have a good
All
one.
right. Good luck, everybody.
I have a question. I came a little late. I'm sorry, Dr. Hughes.
Okay.
I was taking the review quiz. I think the one that you were looking at a second ago for that question.
Uh-huh.
And yeah, it was the enthalpy review quiz. And it was the question about the combustion of methane. I just didn't know how to do the problem, and I was hoping you could guide me through how to do it just so I know like what I'm looking at.
Okay, let me see if I can get to that one. I have a combustion of butane question.
Oh, yep, that's I got it confused, but yes, it was that one.
Okay. Okay, this one right here.
Yes.
So this is a stoichiometry problem that includes the enthalpy change. And so what you do is you convert your grams of butane into moles of butane.
The grams of, okay.
And butane is, let me see if I can write on this.
Oh, the molar mass, is that what you're saying?
Yeah, so this one right here is the butane.
Yeah.
And so what is that? 48, like 58 grams per mole?
I was looking it up. Yeah, 58.
Okay. Oh, I'm sorry. So how many grams? That's what we're looking for. Okay, so first of all, we release this much heat.
Okay.
And so what we do is we take that and we're going to convert that into moles of butane by, oh, this is the worst. So if you came late, what you don't know is that my computer died.
Oh, okay.
It just, I mean, I bought it in 2014. So it was an ancient computer, but it just stopped charging. And you can't have a laptop that doesn't charge for very long at all. And so I have a brand new computer and it doesn't talk to my iPad yet. Okay, so our 6,375 kilojoules of heat, we're going to convert that into moles of butane using a, it's like the mole ratio.
Uh-oh.
Ratio from here. Ooh, did I come back?
Yeah, he came back. Okay.
Sorry, my internet actually totally went out a few minutes ago, and now it's saying I'm unstable. So the mole ratio is 2 for the butane, and 5,314 for the heat.
Okay.
So it looks like an awful looking mole ratio, but we're converting this amount of energy into the moles of butane. And so once you do that, you'll get the moles of butane, and then you use the molar mass to convert it into grams.
The molar mass. Oh, okay. You get the moles and then you convert it to grams.
Mm-hmm.
Okay. That makes sense. And there was also, I think, one before that one that had the 3 lines of chemical equations, and we had to figure out what it was bond enthalpy. It was a bond enthalpy question. That's what it was.
Okay. This could go away. Okay, here we go. You said it was after this or before this?
I think it was before, honestly. I think it was early on in that quiz.
I can't remember if I have them randomized or not. So it might be after it. There has to be a faster way. This one?
Yes, that one.
Okay, so we need to find the enthalpy of the reaction. BrCl goes to Br plus Cl. And they gave us all these equations. So there's only one place where BrCl appears, and that's, whoop, need my annotation back. Okay, and that's here.
Right.
So that is the reactant in this equation. So I'm going to need to use this equation, but I'm going to get it to match that one, I'm going to have to take this one and multiply by -2. I'm sorry, divide by 2, divide by -2.
Okay.
Divide by -2. So it's got to be flipped backwards and divided by 2.
Divided by 2. Okay.
And that'll give us the BrCl. Because that's the only place BrCl is on this whole thing.
Okay.
So I'm just making sure that it lines up in the right place with this equation. And then here's Br gas. So I need to get that to be a product. Well, it already is a product, but it's multiplied by 2. So I'm going to have to divide this one by just a 2. And then here's the Cl gas, and there it is right here. So this one I also have to divide by 2 because that'll give me the Cl gas as a product. But there's still something wrong with this because I have a Br2 liquid right here. And both of these have, this equation only has Br2 gas. So to get rid of this Br2 liquid, what am I going to have to do? This one is going to be flipped and divided by 2. So it's going to be half Br2 liquid. So I need to have this in there to cancel out with it, but it also needs to be divided by 2. Because this reaction only has one Br in it. So since it has 2, but it doesn't have to be flipped because even though it's on the same, the Br2 liquids are on the same side in this list, I'm flipping this one backwards. So all of these reactions have to be divided by 2, and this bottom one has to be flipped as well. So that's what I have to do to get, when I add all 4 reactions together, to get this one right here.
Okay.
And so I have to do the exact same things to the enthalpies. I don't know what just happened. Somebody must have buzzed. That wasn't me,
That was
right?
my phone. Just
okay. So then I'm just going to take this divided by 2 plus this divided by 2 plus this divided by 2 minus this divided by 2, and I should get the right answer.
okay. Yeah, I think I forgot that that was something we could do with delta H, is like manipulate the equations. So, okay, that makes sense.
And yeah, and you know what? I feel like students work this problem by going straight to these things and start like just sort of randomly moving them around to see if they could make it come out to that. And what you do is you start with the reaction that you're given, and you take the first thing in that reaction and look for where is it in the reactions you're given. And then, especially if it's only in one place, in one reaction, and that's usually true, you just do to that reaction what you have to make that go to the right place. Don't worry about, how they all add together. Just think about, where does this have to go to make it match up with the reaction I want? And the answer is, it has to be flipped because it needs to be on the reactant side, and it has to be divided by 2 to get rid of the 2 in that stoichiometric coefficient. And so don't even look at these reactions. Start with the one you're given, and don't worry about all the other pieces. And especially if there's if oxygen is in 5 of them, just ignore the oxygen and work on every other molecule. And then usually the oxygen will get taken care of.
Okay, that makes sense. I wish I got in here earlier. I remembered it was at 8, but I just got back. Had a really long Sunday. I'm trying to look at the other quizzes that I took, the review ones. There it is. Quiz 2. That's the wrong one. Do you have a way that you have I don't know, people have different ways to memorize the quantum numbers and because I reviewed those yesterday and the day before, and I was like, man, I forgot about these.
The quantum numbers. What does N mean? What does S? What do N, L, M sub L, and M sub S mean?
Yeah, and I find that I have a hard time connecting them to electron configurations as well.
Yeah. It's okay. So I feel like what you have to do is look at the periodic chart.
Okay.
See, I need that to go away. Okay. So if you write down 1, 2, 3, 4, 5, 6, 7, those are basically the N quantum numbers. It's the main quantum number, the principal, and it tells you sort of which row you're talking about. Now, there's a little bit of a mess up on the transition metals. So you have to remember that that's the case. And then we have S, P, D. Oh, and I can't scroll up because I'm annotating. Oh, of course my annotations won't scroll. Oh, well, I'll just leave it. It's all right. And then down here we have the Fs. Okay, so this is N, and the S, P, D, F, that's L. L equals 0. L equals 1, L equals 2, and L equals 3. Then L equals 0 only has M sub L equal to 0. So that means there's only one orbital for the S's, right? L tells you what subshell you're talking about, S, P, D, or F. And M sub L is which orbital are you talking about? Well, there's only one orbital for in the S subshell. And so the M sub L is 0. And then you have 2 electrons that can go in there. And that gives you your plus a half, which is the alkali metals, and your minus a half, which would be your alkaline earth metals. Then when you get to P, there's 3 different orbitals with M sub L equal -1, 0, and -1. So there's 3 different p orbitals. That's why we're 6 across over here. So we've got to spin up, spin down, spin up, spin down, spin up, spin down. And then D is 10 across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because D is L equals 2, and we have a -2, -1, 0, +1, +2 for M sub L. There's 5 orbitals, -2, -1, 0, 1, and 2. And each one of them can hold 2 electrons. Spin up, spin down, spin up, spin down. And the spin up and spin down are the MS values, right? Plus a half, minus a half, plus a half, minus a half, plus a half, minus a half. Does that help at all?
Yes, actually very much. I was trying to watch videos and they were not making sense.
I feel like people have come up with all kinds of crazy ways of remembering this. And the thing is, the orbitals and the quantum numbers are what make the periodic chart the shape that it is. And so why don't we just go do it off the periodic chart?
I agree. I learned it this way with Dr. Tournay. And when I tried to watch the videos, they confused me because they had all these other things that they were doing. And I was like, well, I just want to learn it the way that it was taught to me. Just like as a refresher, because this is how she showed it to us too.
Yeah, so like if you have if you wanted to know the electron configuration of like ruthenium, you just back up to the row before it and say, okay, krypton, that's what's abbreviate from the previous noble gas. So krypton. And then you go to where rubidium is. Well, we're in the 5th row, so that's 5s squared, because rubidium and then strontium. And then we're in the 1, 2, 3, 4, 5, 6th column in the transition metals. So that would be 4, D, 6.
Okay, yeah, that makes a lot of sense. That makes a lot more sense. Don't we also need to know the the names of the quantum numbers? Because I know each of them has like 2 names, if I remember correctly.
Well, N is the principal, the main one. L, you can call it they call it so many different things. The azimuthal or the orbital or the or the shell. I'm sorry, the subshell. And this is where it gets kind of confusing. M sub L can be called the magnetic, but it specifies which orbital you're talking about. And they call L the orbital because L tells you whether it's an S or a P or a D or an F. So it's the type of orbital, but that's also called a subshell because the P orbitals, there's 3 of them that make a subshell.
Will it be referred to as angular momentum as well?
The L?
Yeah, because I think that's what my notes says. It says subshell, like you just said, but it also says angular momentum.
Yeah, it is the angular momentum. It does tell you the angular momentum value for that. And I really doubt they're going to use that term because we don't even teach you what angular momentum means in general chemistry.
Okay.
It does come up in my senior class. So just wait 2 years and we can take that one.
And what is your senior class?
Physical chemistry.
Oh, I don't know if I'll have you for that.
Well, if you decide to minor in chemistry, you can do it.
I thought about it.
Or major. You can double major.
I could. I did consider a minor in chem, but it just seems that the bio minor for me is more attainable because I'm environmental health. I don't take very much chem. I think I stop at OChem and that's it.
Yeah, that's the case for a lot of majors. So.
Yeah.
So I hope that helped.
It did.
I really feel like this is the way we should teach it. I don't teach part 1 anymore. That wasn't partly is because one of the other professors retired and they never replaced him. And so the senior class I teach, we used to trade it off, and I would teach all Gen Chem and he would teach the senior class, and then we'd switch. But I can't do that anymore. I always have to teach the senior level class and lab. And so I don't have plus I teach a graduate class. So I don't have time to teach much Gen Chem anymore.
Yeah. I remember that because when people were talking about taking Gen Chem, I never saw your name there. But then when I registered for Chem 2, your name came up. I'd never seen it before because I saw the other names before for General Chem. I was like, oh, well, no one ever told me about this teacher.
Yeah, I only teach this class every spring, and the rest of the time I'm teaching the upper class stuff. So.
Okay, fair enough. Fair enough. I was kind of hoping you taught OChem.
Oh, nope, not in my wheelhouse.
I realized that when I went to look for classes, I was a little sad. I just wanted to keep a professor for like a continuation. I feel like that helps sometimes.
Dr. Russell, I think, teaches part 1 and part 2, and students seem to really enjoy his class.
Yes, and I heard that when I asked, and I registered, and his class filled up within the first, I think, week of registration. So I'm very glad that I did that.
Oh yeah, yeah. He fills up fast, and for my class was full by like 10 o'clock in the morning on the first day of pre-registration, but for some reason it was capped really small. So
really,
that's okay. We made it to the end. So
we did make it to the end.
okay.